In the last video, we talked about how strong acids and bases will completely ionize in water solutions, while weak acids and bases will not, and they will exist in equilibrium with each other. This video will focus more on the interpretation of K. Solubility will also be covered, as it is part of the KSP values. Remember that K equals concentration of products over concentration of reactants, with each product and reactant raised to the coefficient in the balanced equation. When K is large, you expect the reaction to go to the right side, and when it's small, you would expect it to go to the left side, or the reactant side. K is based on a ratio of reactants to products as they move in a dynamic equilibrium. When K is about 1, then there's an appreciable amount of reactants and products present at the same time. This also applies to solubility because the KSP, or product solubility constant, is measured in the same way as Kc, Kb, and Ka. However, we typically ignore solids because most of these reactions begin with them, since they are about 100% concentration, or a constant. Therefore, only the products are left, making it the solubility product constant. When you don't know if a system's at equilibrium, typically a Q value is used. This is to probe the equilibrium system to see if it is indeed at equilibrium. When your KSP value for Q is larger than your KSP value that is accepted at an appendix, then your system should precipitate because the product to reactant ratio favors the reactant side. Changes in concentration, temperature, and pressure will affect a system at equilibrium in many ways. This was outlined by Louis de Chatlier through the Chatlier's principle. Imagine the equilibrium is like a balanced diet, or a balance itself. Its natural process and goal is to make itself balanced, so if something disrupts it, like a change in concentration, pressure, or temperature, it will make adjustments on one side. Since 4 moles of reactant are present on the left side and 2 moles are present on the right, the reaction will shift to the right because there are fewer moles. Since an increase of pressure means a decrease in volume, this leaves more room for the reaction to take place, so they will react to form stoichiometric ratios. For an endothermic reaction where delta H is positive, the amounts of product are increased at equilibrium by an increase in temperature, and Kc will be larger at higher temperatures. For an exothermic reaction, however, delta H is negative, or the enthalpy. The reactants of the products are increased at equilibrium by a decrease in temperature, where Kc is at a lower temperature. If you remove some of your reactant, then your product side will need to toil to make more reactant, while likewise will occur.